Is the recording okay? How is there a limit? You must have some limit.
I've never seen have a limit.
Oh. Age of the universe?
Mm-hmm.
Age of the universe is a limit?
Yeah.
Good. I think we should be done in about an hour. Are you okay still, Nico, with us continuing?
Yeah, I'm fine.
Yeah, because I don't want to abuse any of the time. But on the other hand, I know that some of you are interested in some details. So. And of course, if you have any questions in the meantime, like you already asked me several, then of course go ahead. And, let's see, that's what comes here. Anything else? Okay. Yeah, so I guess, yeah, in about half an hour with that, the system will be set up, then we'll do CCD. So Mark, maybe it's for you, you'll show some programming techniques, I'll show you a little bit of that, okay? You just hang with me. Yeah. I think we'll be done by now, for sure. Of course, many of these relationships will change if we have the three-body Hamiltonian, so then it becomes tricky. But you can see, what I'm trying to lay down here is a principle, how to do it. So if I want to recreate this table, say first of all, for a non-Hamiltonian case, you would say, okay, T1 now starts with the first order, okay? So then T1, which is in C1, would not be second order, but would be first order wave function and second order energy, okay, formally. So then there will be little modifications, wherever T1 shows up, you would have a bit of a change, right? Not much of a change though, because you have to realize that T1, unless you really deviate massively from RP-Fock, T1, although formally being the same order in that case as T2, is still much less important than T2. Okay, so so I guess I don't think this has been explored. In some way, you could think of some maybe dual perturbation series, one for the Q's and one for the V's, because the V operator and the Q operator are really typically different orders of magnitude. That has not been done, but one could think of some sort of extensions of this analysis, right? When it comes to, say, nuclear physics, where you have three-body interactions, right? Again, there will be changes, because say T3 cluster, which shows up here in the second order, will go down to the first order, because you will have one vertex is enough to draw it. Okay? So there will be changes again. Your table will suddenly get a little bit of more, and say, there will be an interesting second order contribution, MVPT2. T3 dagger, VT3. Right? Because T3 is first order. Okay, so you have that. So there will be little changes, right? There. But again, this will be much less important, of course. Well, I didn't say it correctly. It should be VT3, right? There will be something VT3 contribution in the second order, right? Say or let's call it W. The three-body Hamiltonian and T3 in the first order. You bridge them together, you can close the lines, right? Three-body, that's going to be formally MVPT2, actually. Yeah. But it's a very tiny MVPT. So we actually made a point on this one in 2013 with the paper with Robert Roth and Sven Linder and Navratil and others, right? That this, the T3 then becomes a second order, like MVPT2, because perturbation itself is three-body. But then, of course, typically it's much smaller, because for the actual densities of nuclear matter we're using in actual calculations, right? That three-body part of the Hamiltonian is not really, the intrinsic three-body part is not big. There is an effect of three-body on the two-body and one-body through normal ordering, but the intrinsic three-body is not really big. So it will be formally second order, but it will be numerically a very small contribution to the second order. So, it depends how you view it. But the point is to get these principles out. That is, get something like this, and then if you want to work it out yourself, how important is what is the CCS DTQ is bringing to me, and then you have to realize that I showed you one thing. I already showed you that we can lower the costs by simply picking up the leading triples, and in this way, we can mimic the higher order methods by sort of corrections, right? This is a very popular idea, but this table is a real source of motivation. You look at such a table, and you see, okay, what is it I need to pick up to get my theory corrected for a fifth order? Okay, so you are looking at C1, C2, C3, C4, C5, C6, whatever contributions. I see what we lay down, okay, various clusters, and then say, what am I able to pick up? And if you realize that you need, say, Q, well then, can I get some parenthesis Q, kind of a correction due to Q, rather than going all the way within to the 10 scaling of full CCS? You see, that's how you think about it. Once you know these orders, you may pick up some approximations to the full treatment, okay, and that's what many of these methods of parenthesis show. do. Of course, you can also do it iteratively. When I show you the equations, I can maybe comment on this.
That boils down to what you want, right? So if you want energy, I guess my question is, why would you not just do MBPT?
Oh, because then MBPT may not be convergent. For one reason is first, well, two reasons. Well, that's an important reason. Yeah, it's rarely convergent. So in real, in terms of mathematics, I told you, about it, right?
Yeah.
So MBPT is not convergent, but there's more. You see, Kappa cluster picks up more, because it's an infinite order theory with some subset of diagrams. So it doesn't terminate.
The cost of
No, the cost is not. No, okay, that's a good question. Okay, I didn't say about the cost. Okay, so this is a good, very good, very good. If I look at the cost, so MBPT is cheap, of course. MBPT2, MBPT2, that's cheap, yeah? Because if you look at the equation which we derived, it's NO squared NU squared. Okay, but you know, then what is that? But what is MBPT3? Well, actually, it's NO squared NU to the 4 already. It's non-iterative, so it's like one iteration of CCSD. That's the cost of it. Well, you know, this is the same order of magnitude scale. Okay? But you may say, yeah, this is okay. But no triples. You know, without triples, there's no quantitative answer. No quantitative answer. You can get qualitative answers, no quantitative. Well, I shouldn't say that. For some properties, you may be okay. Some geometry you may be optimized with MBPT2. That's okay. Right? But generally speaking, that's not your target method for energetics. And then what is MBPT3 then? Sorry, 4. MBPT4. Actually, there is a problem. The triples cost you NO cube NU to the 4. Those are exactly the parental C triples we are talking about here. Wherever I did it. Because I derived, you know, the triples collections from triples in fourth order. It's the same cost.
Yeah.
So tell me, why would I do that? Give me one reason. Why should I use NP4? NP4 has the same non-iterative. You see, the iterative CCSD steps are cheaper, actually, or cheap, because they are iterative, but they're into the 6.
How long does it usually take? How many iterations does it usually take to converge?
Our code's 20, 30.
Does it depend on the system somewhat?
Yeah, it does depend. Yeah, but we can nail it. Yeah. That's not extreme case. I can go to 50 or something. Usually, we don't have to. I can, and then I'll show you how we solve it and what tricks we impose. Okay. But you know, what I'm saying is that, you know, in the lower, this MBPT prevails, because that is cheaper than anything. That's almost DFT. Actually, cheaper than DFT, because in DFT you numerical quadratures. So actually, DFT may be more expensive. But that is cheaper still. It's one iteration of CCSD, but it doesn't bring you triples. So, you know, you're not moving anywhere yet. To bring triples, you need to go to fourth order, but that cost is already parenthesis T of CCSD. Parenthesis T. So tell them, since the CCSD steps are comparable, you know, they're iterative. So n to the 6 times the number of, say, iterations could be comparable to the non-iterative n to the 7 step. That's the idea, okay? That's how you kind of weigh these costs, right? The n to the 6 is, per iteration is n to the 6, but you do it, say, 30 times, so it's 30 times CCSD for the realistic systems you can study, will be similar to n to the 7. So you maybe double the cost of MBPT4, okay? Well, if I can double the cost of MBPT4 and then I get an infinite order information, why would I do MBPT4? So nowadays I can tell you, if I saw a paper with MBPT4, well, you can imagine what I will comment in my review about it, okay? Things have changed compared to, say, the 80s. The 80s MP4 was a very popular theory. MBPT4 was a very popular theory, okay? But I would say now, you know, motivations are weaker because we have these various ways of correcting CCSD results with similar costs. But the Kappa cluster result is always an infinite order calculation, so it has everything from the fourth order and a lot more. And no extra cost really from the computational perspective. Okay? So that's the thing. It's the thing about triples. You know, if we didn't need triples, suppose the world was without the triples somehow, right? It was created like this. Well then, yeah, we'll be probably doing all these and be kind of done with it, right? But unfortunately, it's not that simple. We need triples to get reasonably quantitative answers, sometimes even more, right? So the question is, how can I bring quadruples at the n to the 7 level? Well, this can be done. We have some levels.
So are these, if we're just doing singles and doubles, I guess, are there some EPV terms that are staying in? Or
Yes,
is
yes.
Okay, so
Always. Yeah, always. This will be another semester. I'll talk to you about to everybody, of course. You know, at the end when we have some time, you know, just shoot your questions and I'll say whatever I can say, given the sort of constraints. I think our constraint is the tape, right? But now Nicole tells me that it can go on forever, almost. Yeah? I have no notion what kind of constraint it is. But anyway, yes, yes, this will have EPV terms and more. Okay? You can try to restrict it to EPV only. Then you end up with the SEPA methods that I mentioned. Okay? So you can do various approximations within. You can take subset of diagrams of CCSD rather than the whole set. Okay? When I show you CCD diagrams, maybe I'll comment on that. There are interesting ideas you can pursue. Once you have a methodology which is so systematic, so well controlled, you can see how well we control it. We have these tables, we can do this kind of thing. We analyze the costs, the floating point operations, we have orders of magnitude, we have relationship with CI. All of this is at our disposal, and a lot more, of course, if you spend enough time studying this subject. Right? All of this is at our disposal, so we can actually start developing methods by throwing away some terms, throwing diagrams, factorizing some diagrams to reduce the cost, going to linear scaling in localized basis. That's, say, our group is one of those who succeeded in this. So we can use our linear scaling calculus to go to games, which is available to everybody at no cost. You don't even have to pay for it. Right? So you see, this is, this, once you have that much of a control, that's why, we like Kappa-Cluster theory. This is one of the reasons we like it. It has so much information that you can control or analyze. Okay? That is really very useful. Not every method has this. We're talking about CI. CI has less flexibility in terms of what can I do with it. I know I can truncate at some excitation level, right? Maybe I can improve on the reference determinant and then, the multi-reference CI. But, in terms of the control checks, there isn't much more. Whereas here we have a lot of sort of these additional gadgets available. So anyway, let's talk about applications. Are you ready? Yeah. Okay, let's take on this one. All right. Well, so what do you do to solve Kappa-Cluster equations? Of course, we always start with the Schrödinger equation. Okay? So, I write it in the normal product form. Remember, we talked about it. Where Hn is the Hamiltonian minus the expectation value of the Hamiltonian in our Fermi vacuum state. Okay? And we remember we can write it as a sum of two terms. That's critical for Kappa-Cluster. Fn plus Vn. It doesn't matter whether you use particle orbitals or not. The Hn splits into the Fn part, the Fock part, and the Vn part. Okay? Please remember from now on, Kappa-Cluster theory is not perturbation theory. We derived it as a kind of a spin-off, right, of Kappa-Cluster, of MBPT. But once you have it, it's an algebraic, it's an independent theory where you have to solve for T. Okay? It doesn't matter whether your T comes from perturbation theory or some other source. I showed you that actually it can come from CI by taking a logarithm of 1 plus C. So it is not related to MBPT so directly. Okay? So, and as a result, I don't have to divide the Hamiltonian into the traditional unperturbed and perturbed parts. I don't have to do that. I'm not going to write it anymore as K0 plus W, okay? Don't have to do that. I know that Hn is Fn plus Vn, and that's how I'm going to stick with it. Okay? And I don't care whether Fn is zero order for some problem or not. Okay? That's the idea. Because it's an independent theory. Well, then the question is, what do I do next? Well, of course, the first thought is to do variational theory. Variational, let's try variational principle. Many people would tell, well, if you want to solve Schrödinger equation, that's what you do. So you write the expectation value of the Kappa-Cluster wave function. Well, let me write it. V0, e to the t dagger, Hn, e to the t, t0. Okay, so this is my wave function. This is the bra wave function. Hn in the middle, divided by the norm. Okay, so it's P0, e to the t dagger, e to the t phi0. Okay? Well, that expression is problematic. Because variation would mean that take this equation and minimize it over the cluster amplitudes in t. Right? The little t coefficients. But if you try to do this, that's a problem because this wave function, even if you truncate t at t1, t2, has a length of full CI. Because you have powers of t. So even when you have so if I say a 10 electron problem, right, then I will have T2 to the 5. It's part of CCSD. So the length of the Kappa-Cluster wave function is always the length of full CI. Well, length of full CI scales factorial with the system size, factorial square actually, right? So that's not a good idea because you may not have a computer to store this vector on. Okay? So we have to do something else. There's another argument that I'll give you. Okay, some already in papers by Čížek, who in 1966 introduced Coester theory well, we say to electronic structure theory, but I would say really he introduced a big way to science, because the previous paper by Coester laid down some possible ideas but didn't work on the equations. Čížek worked it out completely with diagrams and so on and so forth. Classical analysis of the wave function, tables like this, everything is there, okay? And even the first calculations. So, he proposed, soon after that paper, I think he proposed that you can actually work this equation out. I'm not going to do this, because we're not going to use it anyway. But you can prove, actually, that you can vary this denominator into the numerator by replacing the numerator by this. E to the t dagger, hn e to the t. Connected, okay? You can do this. It's a very interesting algebra. I will not go through it, but it's a beautiful algebra that you can invoke. You can simply take the norm and bring it to the numerator when you restrict the numerator to the connected terms. Okay, that doesn't help. That's even worse now. Because now this is an infinite series. It doesn't terminate. Okay? Even when the system has two electrons. You know why? Because, let me sketch it. Imagine that I have t to the n. So I'm going to sketch t as a little block with a line sticking out. Okay? Because I don't need to look at details right now. So this is t, 1t. Typically in e to the t I have some power over it, right? So I'm going to have 1t, another t, let's see, some number of them. Okay? All these t's here. Okay? This is my cluster operator, 1t, t squared, and then t to the, say, let's assume we have n copies of it. T to the n, part of the e to the t. Then I have t dagger. So I have e to the t dagger. So I'll have a similar picture, okay, with the lines extending to the right. Right? Let's see, in e to the t dagger example I have m copies of this. And in the middle I have the Hamiltonian in this formula. Okay? So I'm going to put the Hamiltonian in the middle. Okay? H. H has, say, 1 or 2 or 4 lines, if it's two-body interaction, right? Okay. Look, see, I am asked here to form connected diagrams with no external lines because it's an expectation value, so it's actually C0, right? Well, you see, of course I will contract lines of H, but I can also contract across T with T dagger. And I can do it with an arbitrary number of T's. Even if a system has two fermions, I can have T to the 500 in this formula, because I can connect T daggers with T's fully, okay? That's a non-terminating, we call it non-terminating series, and the thing is that we don't know how to terminate. That is, you can play games and try, but there is no systematic pattern here. There are no a priori how to truncate it, okay? So we have two problems. Variational principle is not a good start, although there is a certain revival in interest in variational Coester theory in recent years, and our group did extended Coester following Ray Bishop's ideas and so on. So of course we are doing things of that and our opponent's ideas. So various people are trying, but the thing is that this is very hard. Hard because of the length of the e to the t wave function, and hard because of non-terminating series. Okay? So what happened historically was this. Of course, many people said, well, this Coester idea is of no use. That's one way to think about it. If you can't terminate it, then I guess it's not useful. But Čížek, Professor Čížek, I should say, okay, who at that time was working pretty much alone as a graduate student in Prague. Imagine, as part of his PhD thesis, on his own, he worked out the whole thing. Okay, he actually was done in '64. The paper was published in '66 in Journal of Chemical Physics. You have the paper in Blackboard. Okay, and that's a seminal paper because he showed that there is a way out of this difficulty, namely by introducing the so-called connected cluster form of the Schrödinger equation. Okay? So what's the idea? Done diagrammatically, okay? He did all this diagrammatically. So his paper in 1966 is, as Professor Rob Bartlett, another important name, very important name in history of Coester theory, would say, it's a crash course on many-body theory, right? In a paper on about 10-20 pages, you have everything that you have here in this course and more, okay? He introduces diagrams, time-independent diagrams, not the time-dependent ones, He proves the connected cluster form of the Schrödinger equation, which I'll discuss. Okay, he compares kappa cluster to MBPT. He compares it to CI, as we did. Okay, and he also derives equations for the approximation called today CCD, just to demonstrate how it works. And then there are calculations in it done in collaboration with Professor Josef Paldus. Okay, so Paldus is not a co-author, but is an important contributor because there are first calculations for the N2 molecule and benzene to do the semi-empirical Hamiltonian N2 denomination. Okay, all of this in one page. So what's the idea? We're going to convert the Schrödinger equation to this form. Let me first write it. Hn e to the t connected phi0 equals delta E0 phi0. Okay. What you see here is a different equation than before. There's no psi naught anymore. There is no psi naught on the right hand side. That's a reference determinant, no? Okay? And we wrapped up the e to the t into this thing called connected operator product. Okay, right now we'll show that this is equivalent to the Schrödinger equation. But what's beautiful about it is that this is a finite series that always terminates at the low order, which does not depend on the system size, but which depends on the Hamiltonian. If your Hamiltonian has pairwise interactions, the highest order term here is t to the 4, even in DNA. Okay? Or Josh's favorite biomolecule. Okay? It doesn't have to be small. If you have a nuclear physics and you have free body forces, this connected product stops at t to the 6. Even if you need to deal with a neutron star. Okay? Microscopic. Right? Nobody's going to joke a little bit. Okay? That's the nature of this equation. So what is this connected product? Well, let me try to sketch it for you. For now. Okay? So I'm going to first let's see how am I going to represent e to the t. We need to find some representation. Of course, eventually we'll work it out in detail. You know, t1, t2, and so on. Right now, I just need some sort of a schematic representation. So what is e to the t? It's 1 plus t plus 1/2 t squared plus 1 over 3 factorial t cubed plus 1 over 4 factorial t to the 4 and so on, right? Let's represent t, as I already did, by a block. Okay? Like this. I'm following here actually what is in Professor Paldus' notes a bit. Okay? Of course we know that t has at least 2 lines, because it's t1, but I don't need to see 2 lines. Okay? All I need to indicate is that there's an operator which has lines sticking to the left. That's what this means. Okay, so what is t squared here in this notation? You have to put t on top of another t. Okay? And if I do this, I don't need 1/2. Because the 1/2 is absorbed by putting this one on top of another. Both are, remember, both are excitation operators. They are particle Hall excitation operators. They do commute. Okay? They are both in normal ordered actual form, you know, x dagger x, normal ordered pairs. Okay? So you can do this. Then 1/2 is absorbed. What about the next one? T cubed. So it's t3, 3 t's now, one on top of another. Okay? I don't need to write 1 over 3 factorial because our weight rules, you remember our weight rules said that when you have equivalent pieces, okay, you can permute these t's among themselves without changing the diagram. You can do it in 3 factorial ways. I can absorb that weight into this schematics. And then t to the 4 will have 4 of them, and so on. Okay? So then the question is this. Okay? Okay, this is a to the t. The question then is this. What is this connected product? Alright? So, well, first we need to figure what's Hn. What Hn, you know already, is Fn plus Vn. So, of course, Fn, it's a vertex, right? I don't know. We use that one, right, for something else probably, right? Do you bother? Is it okay for it to stick it? Okay, I'll use Fn in this one. Okay, and then Vn is, you know very well, this, right? So it's either 2 or 4 external lines. If Hamiltonian has more, there will be more external lines, but it's always a terminating expansion. Okay? I'm going to just write it as this, okay? If you don't mind, for Hn. Okay? We just will remember that Hn has a number of lines going from it. Okay? So what is then the connected product? Well, connected product, okay, These are simply all diagrams where lines of H connect lines of T. Not all of them, but each T has to be connected, each T in this expansion has to be connected with at least one line with an H. That's the meaning of the connected product. So the typical terms in it will be like this. If you start with 1 here, that's just H, right? Then the next one, you take H, and you take the next term here, T. So you connect it with at least one line, okay? There will maybe more lines, okay? You can connect, of course, all lines, that's fine. You can connect one, just one. Enough, one is enough. One means connected product. If there's no line connecting them, it's a disconnected product, okay? Then, of course, you can connect H with the next term, T squared, okay? So you have T and T. That picture tells you all diagrams where each of these T's is connected with at least one line with H. Okay, is this clear? Alright, so then the next term will be Hn. You have 3 T's, right? If I look at our exponent. And then I have 4 T's. Can I have 5 T's? Can I have 5 T's? What do you think?
No.
No, because Hamiltonian has only 4 lines. If Hamiltonian has 6 lines, it will stop at T to the 6, but it's always terminated. Okay? So in other words, you know, this is a sum over, I write it like this, 1 over n factorial Hn e to T to the n, okay? You take Hn cluster T to the n, and you connect it with the Hamiltonian, but you know now that if the Hamiltonian is two-bodied, then this terminates at 4-fold excitations in T, okay? Because you have no more lines to spare in the Hamiltonian. Hamiltonian terminates it. That's what Čížek did. So you see, the first thing is that by proving this equation, Čížek realized that this stops at T to the 4 for two-body Hamiltonians, or at T to the 6 for three-body Hamiltonians. So it always terminates depending on the interactions. Therefore, this is no longer the variational situation where we had a non-terminating series. We have now a terminating series in a natural way. We don't have to worry about that part. So we can derive equations without worrying about how to terminate the exponent. You know, that was the main problem people had. How do you deal with exponent? Some people think it's an infinite expansion actually first. It's not, because we have a number of fermions, so it's a finite, but length is full CI. So many people were very critical of Computational in the 70s. Okay? Because they didn't realize that you can do this. And the paper by Čížek was not yet, you know, in the first few years, you know, it was known to some people, but not everybody. Okay? So it took some time for this knowledge to spread out. And we can also talk about how it spread out there. Okay? Alright, so we know this. So now we're going to do the derivation that is really, I will follow Professor Paldus' notes, a little bit of my own thinking, but it really is nothing else than a modern recreation of what Čížek did in his paper, okay? You know, what I'm going to do is sort of nothing else than a modern presentation of what's in the work by Čížek. So let's work on the problem. Okay, so let's start with the proof. Proof of the connected cluster form of the Schrödinger equation. I start with the left-hand side. Okay, left-hand side of the Schrödinger equation. Hn acting on the wave function. Okay, and we go on. So you have to do the following. You have a Hamiltonian. You have to multiply it by e to the t, which we already know how to represent. I'm going to use this in a presentation. Okay, so it's 1 plus t squared over 2. So those two t's about one above another, plus t cubed. I don't know, add one more. 4 of them. Okay, and so on. All acting on phi 0. Okay? Now we're going to use Week's theorem. Or a generalized form of it, okay? Remember, H is a normal ordered Hamiltonian, so you have to start forming normal products with or without contractions, with all these terms from the exponential. Okay? So what are these terms? Let me start writing them. Well, H times 1. Well, that's just H. Remember, though, that this is now an H acting on phi 0, so all the lines are extending to the left in that H, because we're acting on phi 0. Okay? It's normal ordered form. Then what do you do with HT? You can either leave it disconnected, okay? That is, don't contract lines of H with lines of T. But remember, I put it one on top of another, that's fine. Because lines extend to the left, they are all y-dagger lines. So Hn in this expression and T commute actually inside the normal product. We talked about it already. Because we're acting on phi0. We're acting on phi0. Okay? But I can also connect it with at least one line. Right? So that's going to be this kind of situation. Then I can continue. Okay, let's continue. So then I have T squared. Okay? Well, I can leave it disconnected. Okay? In other words, I'm writing all I'm doing here, I'm putting this in the normal product form with Wick's theorem. But that's going to be just a simple product because this is particle excitation operator. You cannot turn it back here. This is particle excitation operator, and that's Hn with lines extending to the left because you're acting on phi0. Okay? Plus, you can connect now H with a T. Or you can connect H with both T's. Okay? And I can continue. Let's do maybe one more. Okay, so what about the T cube? I can again form a disconnected product, all in normal ordering. Okay, so it's normal ordered product of these four operators, H, T, T, T. Everything put on top of another because we have y-dagger operators, right? They're all commutative. But then I can connect H with one T, leaving the other two inside the normal product form, but not contracted to the H. Okay. Of course, you may wonder, should I connect H to this T? No, because I draw only non-equivalent diagrams. You know, I'm using the diagrammatic form of Wick's theorem. Okay, not an algebraic one. So I have to connect H with this T, then this T, then this T. They're on top of another, so the weight is already absorbed. It's 1/2 of this part. Okay, so I have to do that because we're drawing non-equivalent terms. That's a diagrammatic Wick's theorem. Maybe I should say it. Diagrammatic. But then I can connect H with two T's. Okay, but you have to put them one on top of another to absorb the weight of 1/2 properly. Okay, and then T. And then you can continue. Let's see. Let's keep. Okay, let's continue here. I'll continue here. And then, well, actually, to be honest, I guess I can still squeeze it here with some effort. So, okay, so there will be one more term. H connected to all three of them. To all three, right? I will not maybe draw the 4, T to the 4. Is it okay? Is it clear to you what I'm doing? The next will be H and T to the 4 outside, and H going to be 1 T with 2 T's, 3 T's, and 4 T's, right? So all acting on phi0. So remember, what this means is that each of these diagrams, of course, represents many diagrams because T is T1, T2, and so on, and Hn is Fn and Vn. Okay, so you have to split it into F and V contributions, but they're all in normal ordered form, and they all act on phi0, so lines extend to the left. Okay, with all of this, let's now start observing some patterns. Okay. Well, you can see there is a number of there's a number of terms there. Okay, there are a number of terms there which contain H. Let me use some color to emphasize this. Okay, so there's one here. There's another one here. Because because this is inside the normal product, and because all operators in this expression are y-dagger, you can drop the m symbol. Because we're acting on phi0, so all operators are y-dagger, you can drop the n symbol, so that's just a simple product. Okay? So I really can factor this into H times T. Okay? Is this clear? That's a key piece to understand. This is inside the normal product, we're acting on phi0, all lines extend to the left, so there are y-dagger lines. So you can drop the n, the normal product. Okay? Then this one is not good, but this one is okay. Right, that's H. Continue. There's another one here. Okay? Well, there's more. So what is that we are going to find at H? we're going to find h times. First one is 1, then we have t from the second one, then we have t squared from the next one, then we have t cubed, okay? And then I drop I drop more, okay? But there will, of course, there will be all these pieces where h is not connected to any of the t to them, okay? Is this clear to you? Those are the terms you're going to see in this expansion, okay? All of this will act on phi0, so maybe then I'll say, okay. Then let's look at all pieces that contain hn connected with at least one line to the t. Okay? Maybe I'll use blue now. Not this one, but this one here. Okay? You just walk through your system. Here, there's another one. See this? It's h connected to the t times t. Okay? Can you see it? Something happening? Okay? No, it's nothing. It was some noise. Okay, then let's see. This one here, okay? You see there's ht times t squared. And we didn't write more, but then you end up with the following terms. You have 1 plus t squared over 2 plus, oh, we didn't write it, but it's there, right? Okay, well then we can pick up terms, green, which contain h connected to two t's. Okay, well there is one here. Okay, and if you continue walking through it, there's another one here. And we didn't write enough, but there is a next one which will have this piece and two t's, and this piece and three t's. Okay, can you see it? All right, which means that we have another there, which is h t t, and then you have again 1 plus t squared. I don't know, you write this two of them, and so on. Okay. And if I continue along these lines, you can see that there will be terms where h is connected to three t's. Okay. So if I continue, there will be a term where h is connected to three t's. Okay? If I have enough orange, maybe. Okay? So where is one? We already. So there's one here, right? This guy, right? And you can imagine there will be a term where h is going to three t's and then t out disconnected from it, and then t squared, right? So there will be terms that have this form. 1 plus t and so on. Maybe I have to write it like this, save space. And then there will be, of course, a term where h is connected to 4 t's. If t is in at least 4th power, okay, in e to the t, you can do that as well, right? So you will have 1. Then there will be, if you have t to the 5, h will connect to 4 of them, and t will be hanging around outside it, right? And then you will have terms where t is connected to, if t to the 6, right? In t to the 6, you have h connected to 4 of them, and 2 t's left outside. So you will have the same expansion. Okay, and all of this acts on phi0. Now, is there more? Question to you. Do you think there is more in this expansion? I closed it, so I guess I'm saying I'm done. There's no more, because h is two-body under the assumption of this consideration. So h can be connected with only 4 t's. There is no term where h is connected to 5 of them, because h doesn't have lines to do that. So this terminates. But if you look carefully how we terminated it, okay, well, please note that I produced the terms in the curly brackets are all e to the t. Can you see that? Each one of them is e to the t. What's outside is the connected product. It's h plus h with a t plus h with 2 t's plus h with 3 t's and h connected to 4 t's. You see that? So we can simply write this whole thing, which is the left-hand side of the Schrödinger equation. We can write it as follows. We can say that hn e to the t phi0 equals hn e to the t connected, okay, which is which is, you know, hn plus hn with a t plus hn with two t's, okay, connected with two t's plus hn connected with three t's, and hn connected with four of them. Okay? So that's what you get, times e to the t. Okay? Where e to the t is, you know, our expansion. You know, 1 plus t squared over 2, and so on. Right? Acting on phi 0. Okay? You see this now? That's the read of the right set of backwards. Is this clear? Okay. So with all of this knowledge then, I'm gonna now maybe erase this, and then we are now going to back to the Schrödinger equation. According to this rewrite of the left-hand side of it, we end up with the following equation. On the left we have hn to h e to the t connected, e to the t phi 0. But you see, remember, this is only in the normal product acting on phi 0, so all lines extend to the left. So these parts and the parts in the braces commute. They're all Dagger operators, because we're acting on phi 0. Okay? So I can write it also as e to the t, hn e to the t connected. Okay? I can also write it like this. And then I can write the right-hand side of the Schrödinger equation, which is the energy times e to the t phi 0. Okay? Well, all you need to do now, so what we have is this equation. All I need to do now is to pre-multiply both sides of it by e to the minus t. Okay? Pre-multiply by e to the minus t. And then what do we get? We get hn e to the t connected, phi 0, equals delta E0, phi 0, and we just proved the connected cluster form of the Schrödinger equation. Okay? Which is a finite series. Before I show you the couple cluster equations that come out of it, let me give you another argument, which is algebraic, which actually is already in Koester's paper in 1958. This has not worked out in detail, but mentioned there. Okay, so it is certainly important to say. You know, you can see that the key trick here is write the connected cluster form of the Schrödinger equation, okay, and then pre-multiply by e to the minus t. Well, how about if I start over with the Schrödinger equation for the Kappa-Cluster wave function and pre-multiply by e to the minus t. Okay? Right away. What do I end up with? On the left-hand side, I end up with e to the minus t, hn, e to the t, acting on phi 0. On the right-hand side, I end up with the energy times phi 0. Okay? Well, this suggests, this operator actually, we call it h bar, hn bar, which is a similarity-transformed Hamiltonian of Kappa-Cluster theory, which is a very important object for Kappa-Cluster theory because we use it in every other form of Kappa-Cluster theory, whether it's equation of motion Kappa-Cluster theory or some other methods, okay? So that's a similarity-transformed Hamiltonian, and if you compare this equation with that, there is an implication that hn bar must be simply the connected product of hn and e to the t. Right? Let's try to understand this. Right now it's kind of a superposition, right? So supposition, right? I'm just kind of guessing by comparison, right? Let's understand it. It's very important. Remember in homework I said many times to you that connected means the commutators are connected, didn't I? Remember? I was asking you to prove various equations. Those are simple exercises, but they were all actually had a goal. You know, this was not just that I wanted just to check your skills in dealing with, say, Week's theorem or something. I also wanted to sort of kind of send you a message, right? The commutator is connected. And you can see that it seems to be connected because in one of your homeworks you actually were asked to prove the Campbell Baker-Hausdorff commutator expansion for the transform Hamiltonian. And what did you prove yourself? You had the chance, right? In problem 4 to 7 on one of the homeworks, right? You proved this, that it's Hn plus the commutator plus then a double commutator, right? Over 1 over 2 factorial, and so on, right? And then 1 over n factorial in general H commuting n times in a nested way. Well, okay, so let's try to see this diagrammatically. What is, so Hn is obvious, it's just Hn, so we got it before too. Right, what is the commutator? Diagrammatically, using our schematics. It is an expression where you do Hn times T minus T times Hn. Do you agree with me? Okay, we can now use Week's theorem. What is H times T? It's either you keep them disconnected, okay, or you connect them with at least one line. Well, in this case, I have to keep them disconnected because I cannot turn this line backwards. It's a line that goes this way. Okay, this is so the particle and whole lines here. So meaning that I'm subtracting the product only. You see what happens? The disconnected parts cancel out, and you end up with this. But this is a connected product of Hn and T. Okay. How about if we try one more? Because I guess enough is enough to do one more. Okay, let me do one more. Okay. Coming all of it. Okay, good. All right. How about the HNT and commuting with another T? Okay, the next term in commutator expansion, right? So we already know what this one is. It's H connected to the T, right? So I don't have to work this one out. So what I end up with is this. It's Hn T times another T minus T times a commutator of H and T, which we computed to be a connected product, right? And then 1/2 in front of all of this. Right? That's what it is. Now again, I use Week's theorem. The first term will give you two contributions. One of them will be just keep these two terms disconnected, so H and T times another T. Okay? Plus, now please watch this carefully. This T precedes this T. So I cannot put them one on top of another when I start connecting, because this was already connected. That's my second connection of the T behind the previous one. So it's actually something that looks like this. T here, and then other T is this. Okay? That's the original T you had connected already. That's the new one you're bringing. Okay? And then you subtract here again. I cannot bend these lines over. So I just end up with a simple product of H and T and T. Okay? Once again, the disconnected parts cancel out, and I'm left with this guy. But you see, I can vary the 1/2 by putting these on top of another. Those are our diagrammatic rules. So I end up with H, T, T. But that is simply H n T squared connected 1/2 in front. You see this? So in general, if you follow this argument, it's really easy to show that it's very easy to show. Can I, let's see. No, I should not. Yeah, maybe I'll write it here. No, okay, I'll go back here. It's easy to show that Hn T commuting with another T and so on. You do it n times. And you take 1 over n factorial. That's the same as Hn e to the T, sorry, Hn T to the n connected 1 over n factorial. Can you see this? Which means that if you use the Campbell-Baker-Hausdorff expansion that I started using here, you end up with connected, connected, connected and connected up to 4 times. You cannot continue connection because H does not have more than 4 lines. And actually this might be an exercise for you, just to practice, if you want to practice this way. You can just actually prove that the 5 commutators is 0. Commuting the 5th t. After 4 commutators you have no lines to, you know, to spare in a way. But algebraically actually you'll see that the H t to the 4, I mean H commuting 4 times, commutes within a 5th t. Okay? So it terminates algebraically as well. Okay, people knew that. But you know, you can see it on diagrammatic, right? So we are learning now that if you apply the algebraic trick of the commutator expansion, then a to the minus t, h and e to the t is indeed a sum of 1 over n factorial, h n t to the n connected and going from 1 to 4. 4 because we have 4 lines in h, okay? And of course this means that we just proved that similarity-transformed Hamiltonian and the connected product of h and t are the same thing. Okay? So here we are now bridging the work by Coester and Čížek together in a single consideration. Okay? So now, is this all clear to you? This is actually, you know, already Coester said because of this, because you know he writes his paper is very short, but he has very nice statements in it. And so he says already, well, if that's the case, if you look at the Schrödinger equation, the connected form, you see size extensivity in front of your eyes. Because you have connected product here. Your energy can never be disconnected anymore. You are recreating the entire MBPT series in one shot by solving this equation. And you end up with size extensive results. Okay? Because we did this trick with the connected form of the Schrödinger equation. Okay? Do you appreciate? This is extremely important intellectual step. First mentioned by Coester, because he wrote the paper and says, why do we bother with this complicated, well, didn't say it, because he was very polite, but at least, why do we bother with this MBPT theory, which I can recreate the whole MBPT from this equation? You know, he wrote an algebraic with similarity-transformed and commutator expansion. Okay? But he said this. I can recreate it, because if I start iterating this equation, I start generating MBPT. Okay? So he says, essentially his paper is about how to do MBPT in an easy way. Right? Without doing this order by order. Okay? And then of course Čížek followed through. Okay, so now we have to set up the equations. How do we solve Computational equations? So we know that our starting point is the connected classic form of the Schrödinger equation. We're not going to use variational principle. We use another alternative, which is a projection technique. Okay? We start from this equation, and we now do the following. When we project, so let's write it here. We project on phi0 first. Okay? What happens? On the left-hand side, I have phi0, hn, e to the t, connected phi0. On the right-hand side, I will have delta is 0 and phi0 overlapping phi0, which is 1, because phi0 is normalized to unity. That gives me the energy formula. We'll work it out in a second. Okay? How do I obtain the t operator? You project the Schrödinger equation on the excited slated determinants correspond to what's in t. Okay? So in general, we're going to now project on excited determinants, and I will write the general case, n tuplet excited determinant. Okay? And we can obtain on the left hand side phi I1, In, A1, An, you see I'm copying from here, Hn, e to the t connected, phi0. What do I get on the right hand side? You can tell me maybe. What do you think I get on the right hand side? If I project it on excited state determinants as I am doing. What do I try right here?
Just get delta E0.
What exactly are we?
Wait, it's 0.
0. Because excited slated determinants are orthogonal to phi0. So you have nothing on the right hand side. You see, that's a much different proposition compared to CI. Energy is not part of the calculation. Okay? You see the philosophy of Kappa cluster, and of course you do it for, you know, for ordered sets typically, okay? Because you're not gonna repeat this for linear dependent sets. And you do it for what n values? Well, it depends where you truncate. Okay? Whatever's your truncation. In full CI, you'll go all the way to capital N. In approximate methods, when t is truncated, I will stop at, say, some m, which, of course, generally speaking, less than or equal m, right? That's how we set up these equations. So that the number of equations equals the number of unknowns. Okay? So, for example, and we're going to now derive this equation. If we go beyond perturbation or something like this, is it okay? Unless they throw us out, then of course we're done. Hopefully not. Okay? Because I would like you to see, we're so close now, right? So what would be the CCSD? So let's just write something that we already, just as an example, e.g. So if t is truncated at singles and doubles, I need equations for amplitudes TAI, remember, single excited amplitudes, A, T1I, and double excited amplitudes, right? AB, T2, IJ, anti-symmetrized, we have the notation for it, TAB, IJ. I need equations for these. So what do I need to do? Project the Schrödinger equation on singly, doubly excited determinants. So I consider equations like this. Equals 0. I consider equations like this, where you project on doubles. Okay? And you stop. Because now the number of equations I have equals the number of unknowns. So I'm decomposing the Hilbert space, decoupling singles and doubles from the rest of the Hilbert space. Well, if we had another, say, 10 classes, I will show you that that can sometimes is a problem. Okay? Right now, I will tell you it's okay. All right? That's how we do it in the standard conventional Computational theory. So for triples, I guess I'm not going to write it, but I guess you know what to do. You would stick T3 here, and you would add one extra system of projection on triples. That's how you do it. For quadruples, T1, T2, T3, T4, project on singles, doubles, triples, quadruples. That's how we build the hierarchy of Kappa cluster approximations. So now the question is, what are the detailed equations that we want to solve? Because I hope that, so you'll see what is that we're doing when we write these programs. I got a message yesterday signed by Mark Zuckerberg. He says that we don't have enough programmers in the United States because we have 500,000 open jobs right now in the computer industry, and we're producing only 50,000 graduate students in computer science in this country. So where to find the other ones? So I guess, okay, I hope that the two of you are in this category. I will have to help Mark Zuckerberg and people like this. Right? They are right. How can we keep this economy going if we don't have enough people who can write programs, right? There's your question. Right? Same in quantum chemistry. Don't have enough people.
There are too many people writing programs.
Yes,
already.
yeah, but we have to really shake up ourselves and understand this. Or we lose competitiveness. We'll be buying programs from other places soon, right? That's the way it is. The economy doesn't tolerate vacuum of this sort, right? It's a serious problem. It's an interesting problem. It also applies to quantum chemistry, to infrastructure theory, and other theory. You have to find people who can write these programs. Okay, anyway, so let's start with the energy. Energy is phi0, you will see something cool now. Hn e to the t1 plus t2 plus and so on, right? Connected phi0. So right now I'm going to derive the Kappa cluster energy for a general case. No truncation in T. Okay. We need to do this, so maybe I'll say here, energy, right? Correlation energy, of course. Right? No understand. Correlation energy. Okay? How do we do this? I have to realize that we have Hn, which is Fn plus Vn. So I write it diagrammatically as F plus V. Okay? No labels right now because no need. Okay? Or maybe I should actually. Okay, now PQ, PQ, RS. You know it already. And you sum over PQ and PQ RS. Okay. How do we represent cluster operators? Well, I already kind of gave you an idea how. So T1 will be, if you use the Hugenholtz representation, it's going to be something like this. And it's an operator where you're summing over I and A, okay, and you're exciting one whole into one particle, right? What is T2? It will be a circle with 4 lines, okay? A, I, B, J, okay? And T3 will be similar, right? 6 lines, all right? If I need to deal with it. I'm not going to deal with it too much today, so, but in case you need to see it, that's what you would do. A, I, B, J, C, K, and you sum over. You can see that these are good equations because T1 is T, A, I, E, I, A. I would like you to get used to the reading of it. We're not going to be reading this as so far. We're going to be, because we're putting the bra as a subscript, ket as a superscript. So the way you read a diagram is outgoing line into the subscript, incoming line into the superscript in the matrix element. That's how we're going to be reading from now on. This one is 1 over 4 T, A, B, I, J, E, I, J, A, B. Okay, I'm not going to write, you remember, Einstein summation convention. I'm not writing sums, but they are there implicitly. Because we are using Einstein summation convention, we repeat the upper and lower indices. So 1 over 4 is fine. We have these two lines, A, B, and I, J are equivalent. So we have 1 over 4. Those are anti-symmetrized, remember, anti-symmetrized cluster amplitudes. And those are excitation operators. Okay? Okay, with all of this, let's derive the energy. So if you look at it, what I need to do is the following. I need to write, well, there will be terms like this, P0. First, let's pick up the Fn term. So Fn times 1 plus T1 plus T2 plus so on, plus 1/2 T1 squared plus, you know, T1, T2 plus, and so on, right? So I just pick up some. Okay, not necessarily all systematically, right? And I have to form a connected product. Remember, Hn e to the t connected means that I have to take the F vertex from the Hamiltonian, I have to take contributions to e to the t, and I have to connect them. That is form a connected product. Okay? And I have to do the same with V. So maybe I'll leave a space, because you will see not much left. Then I have Vn again, the same thing. Right? So we have 1 plus T1 plus T2 plus, maybe here, I'm exaggerating. 1/2 T1 squared plus, T1, T2 plus, T3 and so on, right? You can also put here T3, okay, all these other terms, right? And we have to take V and connect it with at least one line to these cluster contributions, okay? But see, you cannot do much, because F has only 2 lines. So first of all, one will, I ask you, do you think one will contribute? No, why? Because Fn cannot be, it's a normal product form. Expectation value of the normal product form of an operator is 0, so no 1. 1. No 1, okay? What about T1? You think it will contribute? Yeah, there will be a diagram. So let's write it. So it's going to be a diagram like this. Right? I connected F with T1, okay? And of course I can put A and I, and that's my diagram to read. What about T2? So this one is in. What about T2? You think I have to draw it? No, you have to form connected product with no external lines. T2 has 4 lines, Fn has 2. So this does not contribute, and if you continue, nothing else contributes. You're wasting your space. Okay? See, that's how it goes. It looks like a complicated expansion, but almost nothing survives it. And that's not an approximation, it's just diagrams. What about this guy? Do you think 1 contributes here? No, because it's Vn. What about T1? Can we do something with T1? But not fully. You see? Not T1. Not with Vn. It will be in equations, in other equations, but not here. Okay? Because we cannot fully construct it. So again, T1 goes away. What about T2? I think we can do something finally. Right? So it's going to be this diagram. Right? VT2. So this is, maybe I should say, this is Fn T1 connected. This one is Vn connected to the 0. This is Vn T2 connected. Right? And of course you have to put some symbols. A, I, B, J. Okay, what about the T1 squared? Can we do it? Still can do it. That's right. So this one is fine. This one is fine. 2 T1s, one on top of another. And your V is connected to both of them in this way. Okay, A, I, B, J. What about next ones? No, too many lines. Okay, not much survived. Okay, so you see when it comes to energy, the energy of Kappa-Cluster theory equals only three contributions. Okay? So the energy equals Fn connected to T1 fully. Okay? Vn connected to T2 fully. So I write that's C0 plus 1/2 Vn T1 squared connected here, right? Of course, you can put it in phi0, so it doesn't look weird. But that's all there is to it. Now you have to just read these diagrams. Okay? So I'm going to use again the notation that I would like to stick with. So, you know, before when I did a Fock matrix element, we have an Fn. So when we read these diagrams, we have to read the matrix element. So what is Fpq? That's, you know, for a diagram that looks like this, right? Right now I'm going to switch gears and I'm going to write it as bra to the bottom, q to the top, so that I can continue using my Einstein summation convention, or my Einstein's summation. Okay. All right. What about V? Same thing. You know, we used to write anti-symmetrized matrix elements in this way, right? And that was fine for the duration of the course. But right now, I'm going to write it like this. The bra symbols go as a subscript. The cat symbols go as superscripts. That's how we're going to read it. So you see outgoing lines here, incoming lines here. Okay? That will be much neater, as you will see. Okay? So with this, let's read these diagrams. So the first diagram, you know, no need to, this is how, of course, these are Hugenholtz diagrams. That's obvious, right? I didn't do it. So Hugenholtz. So the weight of it is 1. The scalar is, outgoing line is I, incoming line is A. That's how I read it now. And for the cluster operator, I have T, A, I. And I'm done with the first term. Sum over A, sum over I. Plus, the next term. What is the weight of this diagram?
1/4.
Yes? So it's 1/4. Now you have V. Now, of course, we need a Brandow to get the sign right. Okay? So I will do the Brandow here. Okay? It's going to be, of course, something like this. This is my T. I will always expand the circle into an oval, like this. Okay? So that's your diagram. Do you agree? Okay. So the weight is 1/4. The sign, two loops and two internal lines, so it's plus. And you read it like this. V, outgoing lines are ij, incoming lines are ab. And then you multiply by t, ab, ij, sum over ab, ij. I'm done. And the next one. What is the weight for the next one? This guy?
1/4.
This is on top of another?
1/2.
1/2. That's Kappa-Cluster. Okay, 1/2. Good. 1/2. But the rest, you know, again, you need a Brandow. Is it okay if I just squeeze it here? Somehow? Okay. That Brandow will be something like this. A, I, B, J. Okay. Sign is plus. Weight is 1/2. Matrix element is I, J, A, B times the product of T's. So you have V, I, J, A, B, T, A, I, T, B, J. And we're done. We demonstrated this is a formula for the Kappa-Cluster energy. But the formula does not depend on the level of theory. You see that? I never had to assume where T's are coming from. T3 does not contribute to Kappa-Cluster energy. Because the Hamiltonian is 2-body. If it was 3-body, we would have T3 in it. So how do the higher order clusters contribute? Because that confuses people. You say, yeah, wait a minute, so CCSD is exact? No. Because you are solving for T1, T2 in the presence of T3, T4, and so on, all these other terms in the equations. So this is a different philosophy. When you solve for T1, T2 in the absence of T3 and higher, that's CCSD. Then you end up with this equation will give you CCSD energy. But if you solve for T1, T2, that's all you need for energy. If you solve for T1, T2 within CCSDT, now that's a different value of T1, T2. That's how we are dealing with energy in Kappa-Cluster theory. The reason we call it coupled cluster is that all these T's components are coupled in those equations. Okay? So T1, T2 computed in the presence of T3 is different than T1, T2 computed in the presence of T3 and T4. You know, if you retain all these terms. Okay? And so on. All right. But of course, there's one specific case. Maybe I should mention. Look, if this is, imagine that this was Hartree-Fock. Can you tell me which term? You know, you had a question in midterm. Which term drops out when this is Hartree-Fock calculation? Calculation is based on Hartree-Fock orbitals. What goes out?
The first one.
Yeah. So for Hartree-Fock, this is gone, and those two will be left. What about if I have an approximation which we call CCD? Capacitance doubles with T1 is 0. That's right. Only middle term survives, right? So you see, so the only sort of deviations from this would be CCD, you only have the middle term, and CCSD in Hartree-Fock, calculation in Hartree-Fock basis would eliminate the first term.
So most of the time you don't even look at that first term.
Huh?
So most of the time that first term is
Always, my advice to you, programming this, if you like, always write the program even though this is going to be numerically 0. Because if you never converge these things completely. So if you converge your t's to say 10 to the minus 7, there will be some left over of diagonal matrix elements. You know, sorry, if you converge Hartree-Fock equations, first of all, you never converge them completely. So there are some remnants of FIAs which are not entirely 0. They may be 0 from the physical point of view, but they are still non-zero. Okay, and so my advice is code it as it is, and don't worry about it. It costs you nothing in terms of computing power. Energy costs whatever, nanoseconds, whatever is the speed of clock. Right? Okay? No need to worry about it. Okay? My advice, don't drop it because you are using Hartree-Fock orbitals. Because you want to make your program general purpose. So you can use it for Hartree-Fock orbitals, for non-Hartree-Fock orbitals, for converged Hartree-Fock orbitals, for not so well converged Hartree-Fock orbitals, and so on. You want to have all these options. Okay? Just code the whole thing. And then it'll be good. Alright, how about the equation? So we already know the equations, the recipe. We're going to now work out, if you don't mind, CCD. It's about 10 diagrams, not a lot of work. But you're going to see them in the full glory. And Nicola, you're still okay?
Yeah.
Yes?
Can we take a bathroom break?
Yes. So how about if we have a bathroom break and I erase it in the meantime? Bathroom or some other break, or drinking break, eating break, whatever break you want to have. You can of course eat as I'm talking, okay? It's fine for me to eat. My mother told me that you should never talk when you eat, right? Or something like this. And she told me this when I was very small, so I tried to keep that. Right? So I'm not going to do this, but you are not talking all the time, so you can certainly eat. Please go ahead, yeah? I may need a little drink, maybe. Is this clear so far? All of this stuff that I said? I mean, the philosophy and all this. It's a different, but always appreciate. Kappa is not like other theories in that sense, right? You can see we're not using variational principles. So of course, there's always a question what happens if somehow, I lose the bound property, right? It can happen. And we have all kinds of issues with it, right? But the thing is, of course, also that this is different. We're talking about nonlinear systems of equations, okay, which do not contain energy. Please note that that's a fundamental change compared to everything else. In CI, you're solving an eigenvalue problem. Wave function and energy at the same time. In Kappa cluster, of course, there is a benefit. The left-hand side, h times c of CI, is a linear problem. Kappa cluster problem is not linear. Okay, so you pay the price for using the exponent, right? But I also already told you, these equations can never be more complicated than e to the 4. If you're having those 2 points, okay? So, and you will see CCD has no more than quadratic terms. Isn't that bad? Okay? CCSD has the highest terms, T2 terms are T2 squared. T1 goes with 4th power. Okay? But T2 comes with the 2nd power only. Alright? So, it is simply, exponential kind of scares people a little bit, right? Because you get this impression as if we need to worry about some infinite expansions or some complicated nonlinear algebra. No, it's not complicated because Hamiltonian fixes the problem for us. Okay? All right.
Practical question. How weighing accuracy, how important is higher levels of CCSD, T, Q, whatever,
Yeah.
versus having different reference states?
Oh. Okay, I have actually a simple slide showing this, so depends, what's going to happen to us in 20 minutes, but the answer to it is that there is not much of a dependence, roughly speaking, because of Fowler's theorem. You see, Kappa-Kassan ansatz, it's not a linear ansatz, it's an exponential ansatz. So when you think about it, okay, when you act on phi 0, I can kind of write it like this. E to the T2 and higher terms times e to the T1 acting on phi 0. But you know what e to the T1 does to phi 0? It rotates it. We proved it. That's Fowler's theorem. So that's some sort of, we can call it a new reference. Of course, T2 and higher are still represented using the original reference, so it's not exactly invariant, but it is numerically invariant. And I have examples. It's an amazing theory, right? Because Fowler's theorem is built into it. So you don't have to spend as much time on optimizing orbitals as you have to in CR. That's a huge achievement to have a theory which has so much of an environment. And of course, the higher the better for CCSDQ. I mean, there isn't almost anything you can do to do the structure. CCSDQ, for all practical purposes, is an exact theory. Okay? There isn't much more in chemistry. And I think certainly in nuclear physics, there isn't much more than CCSDQ. If we could today keep solving CCSDQ all the time repeatedly, I don't think it would be much more interesting these fields, right? And if you could do it with linear scaling, there would be no need for DFT also, right? So we would be doing things. But unfortunately, it's not that simple, right? CCSDQ has its cost, so of course the fight is how to bring T3, T4. You can imagine, because of this, the big fight, big battle, right, or whatever, is to how to bring T3, T4 with less than CCSDQ requires, intelligently by some tricks. Okay, but that knowledge, that was the table. The table tells you what you need to do more or less, right, to be accurate, and that's how we think about it. Okay, so let's do now a specific theory. First, the general recipe. So what we need to do is to solve equations that look like this. We have n-tuplet excited determinants. We have hn e to the t, subtraction here, phi 0 equals 0. What this really means that I really need to consider something like this. Imagine, what I do is this. I will do first some sort of block sketch. I take Hamiltonian and I connect it to e to the t. Right? And I have to make sure that the lines that are sticking out of it match the lines of this projection. Right? Projection is, remember how we represent the projection. So I'm going to write it, let's see, what do I have here? I don't know, some sort of a ball like this, right? Sorry. A1, I1, AN, IN. Remember, these A, I indices are fixed because we're projecting on a specific determinant. Okay? So we really, if you think about what these diagrams are, schematically, that's what they are. Form diagrams from H, E to the T, and make sure that they have lines that are matching the lines of the projection. Projection is not bringing anything other than the indices, really, because the scalar factor for the projection is 1. Right? Well, there is a thought in this then. Because that is that how about if I just learn how to draw diagrams of H, N, E to the T connected, and make sure that these diagrams have external lines A1, I1, AN, IN matching the lines of the projection. Right? That's what is being done. What I'm showing to you is what is really being done by the developers of Kappa-Cluster methods. Every program in the world that you see is written in this way. Okay? What you do, you consider diagrams of this part with external lines matching the lines of the vertex, because that vertex just brings you, indices, nothing more. So it is not worth drawing even. But you have to be careful, okay? So we're going to be drawing this part only, but you have to be careful, of course, because you have to figure the sign factor. This is all still in the Hugenholtz form, and everything depends how we're going to deal with the sign factor. So let me just give you an idea how to do this. Okay. In general, when I have a diagram with this sort of box feature, it may happen. Okay, so let me start with the one I already showed you. So we agreed, I guess. Okay, this is still a Hugenholtz diagram right now. That one of these diagrams has to look like that. But of course it may happen that if you start flipping indices, remember they're fixed. What if I replace A1 by A2? It will still, lines will still have the same labels, but they will be arranged differently, and this may be a different diagram. And it's hard for me to convince you 100%, but you'll see it in a moment. We'll see the equations, okay? I'm just saying that what you have to do when you do this trick of dissociating the vertex of the projection, you have to watch out for the fact that permutation of the A and I indices, because they are fixed, may produce new diagrams. Okay, so suppose we have another diagram here, okay, which is labeled such that now I have some permutation in general. Let's assume that that diagram is different than the original one. Okay, so I have some permutation E, AP1, AP, and remember the permutations, right? And IQ1, IQN. Okay, so P and Q are permutations of indices 1 through n. Well, then the question is, what is the consequences of course, you're still connected. Remember, you're still connected to the same. I don't draw it, but it's obvious. We still have to connect it to this guy. Right? We just got to drawing this guy, but it's there. So in order for me to do it correctly, the next thing I should do go to Brandow's. So let me try to sketch the Brandow for this one. Okay? Well, let's assume that in this diagram, loops, the way I expand it is such that I1 enters the diagram and leaves it as A1. Okay? Let's assume that that's going to be, that's the way I expanded my vertices. Right? And then, again, IN enters the diagram and you leave as AN. Okay? Why, so let's assume this. Of course, here the situation is straightforward. What I need to do with this, remember, there's this vertex here, which is invisible, right? But it's there, the projection vertex. A1, I1, AN, IN. So I also have to expand it. When you produce Brandow, everything has to be expanded into Goldstone form, right? So the leftmost vertex will be like this. Okay? That's my A1, I1, AN, IN. Is this clear to you, what I'm doing? Okay. So let's, so this is kind of like maybe this way, right? Let me put this up maybe. And then we can, well, actually, sorry. No, maybe I should do it. Yeah, I'll be rotating the paper, flipping back and forth for a moment. But, yeah. Let's try to figure the formula for what we have. So if I want to, what I'm saying is this, I don't want to draw this projection vertices. So if I do this one, what is the sign factor? The key will be the sign factor. We can, there is no matrix element here. Scalar is 1. So I get all the scalars, all the operator part, everything, sorry, there's no operator part to the projection, right? So all the scalars are read from this block. The only thing that you can read from the block sort of carelessly is the sign. Because by dissociating this vertex, you may change the sign. Okay? So what's the sign? It's -1 to the number of loops. Okay, first let's start with the block. So imagine that we have the number of loops in it is L. L loops in it. Okay? Then I have internal whole lines in it. H is the number of internal whole lines. Okay? Okay? In this block. But you see, by connecting it back to the dissociated piece, the number of loops will change by n. You see, because when I connect it into a loop, I'm going to get an increase in the number of loops compared to this guy by n. 1 up to n. Is this clear? What about the internal whole lines? How do they change? First, I count the lines in the block. Then I'm saying, what happens when I connect it? How many new lines will emerge? N. You see? That doesn't change anything. I can get the proper sign just from the block. I don't need the leftmost vertex to do this. Well, but let's go back now to the other. Okay, I will flip it again, and I think we'll be done with flipping for this one. Okay, what happens here? Well, here, your block will be now having permuted. Okay, and imagine that I'm doing this so I expand it in the same way as this one in terms of the loop structure. Okay, but because I permuted indices, this is not going to be A1, it will be A with some permuted one. I with permuted one, okay? So what you end up with will be A P1 here, I Q1 here, right? I hope I called it this way, right? And then dot A Pn here and I Qn here, okay? But the loop structure will be the same, because all I did to produce this Brandow compared to this one, I expanded it the same way as here, but because indices are permuted, so they will remain permuted here. But not for the Brandow representing the projection. That one has to be always expanded the same way, not to produce some mess with signs. Okay? So here you still expand it as A1, I1, not permuted. Okay? And the question then is, how will the sign rule work here? Well, okay, I'll show you now very quickly that this is. You count the loops here, you count the holes here, just like we did before. What is the change in the number of loops? It's going to be, you see, it depends now. We don't know this actually, right? The number of hole lines, we know how it changes. Because you're going to still reconnect the same way, so you'll end up with n extra lines. Okay? So the delta H is n, but the delta L is not clear because it will depend on permutations. Okay? Well, you will learn now that the sign will be the sign of the permutation of P, sign of the permutation used for A's and I's. Okay? Let me illustrate this. This is very simple. Imagine that I have, let's see. Imagine that imagine that I have my block, all right, this is my projection, okay, and I have A1, I1, A2, I2, and so on, and then AN, IN, okay? Let's look at the block. Hn e to the t connected. Okay. So what I have here, let's assume that my permutations are P is identity. I'm not permuting the A symbols. I'll permute the I symbols. So my Q permutation will be permute 1 with 2. Just permute I1 with I2. Okay? Let's just do that. So what's going to happen is this. You know, you have your loops. Okay? But now this is going to be A1, this will be I2. Okay, this will be A2, this will be I1. And then this one will still be, my example is simple, I'm not touching the last one. Okay, when I now connect them, let's use some color. You see, A1 will connect to A1 here. Now it will retain as I1, but not back where here, it has to go down here. Then you go through a diagram, and return with A2 here, and then with this I2, return to I2. You see? The number of loops in this particular case, if you write what is this, so delta H is still n, but the delta L is n minus 1, because of the permutation. So you see the number of loops depends on the permutation. So you can see that if I made one interchange, I change the sign by 1. Every interchange will produce a sign change. That's why there is this rule. So you see, now we've learned something magnificent, and now we'll just apply it. In order to derive couple cluster equations at any order, you draw diagrams of H e to the t connected with as many lines as the projection is, and label them with indices of the projection. and you can read this, everything from that part. You don't need to draw projections. You just count the loops, count the internal lines, and you apply the permutation that goes from canonical ordering, I, A, J, B, and so on, to a non-canonical one. Okay, that's all. Okay, so let's do it with CCD. Okay. CCD is the oldest couple cluster theory in terms of its implementation. Okay, this was already done in 1966 by Professor Jerzy Čížek. Okay, he didn't call it CCD. The term couple cluster comes from the much later papers in 1970s, 76 or 7 more or less. The first people using it, the first person using it as far as I know, was Professor Frank Harris. At that time at Utah, right now, oscillating between Utah and QTP in Florida. Okay? And then Henk Monkhorst, his good friend, Professor Hendrik Monkhorst, used it also. So then we started using couple cluster. But Čížek didn't call it this way. So he actually called it coupled pair many electron theory. The MET came from the work by Sinanoglu. I think the G has a, oh, this, I don't remember now, sorry. The moon shape, yeah, of the Turkish alphabet. So at that time a professor at Yale, okay? And this was MET theory. The couple categorization of it is called CPMET. That's how Čížek called it. When he added T3, he called it extended CPMET. So this was kind of a difficult acronym, sort of idea. Then eventually people came and he said, well, that's specific. Ron Barker was very instrumental. He said, well, okay, no, let's not write it this way. Let's have CCD, CCSD, CCDD, Q, just use those letters, keep, and use CC in front, so it will be clear what you're doing, right? So that became eventually very systematic. Okay. So what is CCD? That's a theory where T is T2. So our equations are very simple. We just have to project the Schrödinger equation in a connected form with T2 in it on doubly excited determinants. I'm not deriving energy formula because we already did. T1 is 0 there, so only the middle pair will survive, okay? How do we do this? We are being told we need to derive equations like this. We have to derive diagrams of this form and make sure that they have 4 lines sticking out of them. Okay? Or permutations, right, of those. Okay? So let's do it. So I'm gonna now, if you don't mind, I will erase now the right part. I need these two left to finish it off. Okay? Actually, oh, there's one space here. So let's start writing. So what do we have? We have phi, I, J, A, B. And we'll do it, using our recipe. Skeletons, non-oriented skeletons. Then we're going to throw arrows and indices, and then we'll go from Hugenholtz to Brandow, and then we'll read it. Okay? That's how the schematics goes. Alright, so we have Fn times, again, 1 plus T2. Remember, there's no T1 now, so I don't have to worry about it. I just have to start writing powers of T2. Okay? You have to form connected diagrams, and then that's your Fn contribution to the problem, right? What about the Vn contribution? Phi, I, J, A, B. Vn, 1 plus T2 plus 1/2 T2 squared, and so on. Connected, Phi 0. And this has to be 0. Okay? Those are the equations we need to derive. Okay, let's analyze. Again, I'm going to use my red chalk and you'll tell me what goes up. One much left, as you will see in a second. Do I keep one? No, because this is one body, this is two body. One goes away. What about T2? Well, I guess we'll watch it. Okay, so maybe we'll keep it. What about T2 squared? Maybe I'll just ask the next one right away. Do you think we have to keep it there? No, yes, because, yes, no, that's right. Yeah, because, T2 squared is this. You have to form a connected product. Remember, the word connected product means that you have to take lines of F and connect to both. That's a connected product. But F has no more lines. Okay, connected product means connect F with T. Not with one T, with both T's. Remember when I was deriving this connected product, the connected Hn to the T. Remember that? Hn, you have to connect every T that you have with the Hamiltonian. So I did. But you see, I have no more lines to spare here. I have only 2 lines left. It should be 4 lines. I don't have 4 lines. It should be 4 external lines. So I don't have it. So that goes away. That means that this also goes away. So I'm left with the middle term. Okay? Well, let's see what diagram is there. Well, the skeleton is very simple, right? You have, that's your skeleton. That's the only one. With 4, remember, there must be 4 external lines. Because we're projecting on ABIJ. Okay, let's continue here. Do I need to keep Vn? The bare one? Oh, I do. I am projecting. Remember, now it's not phi 0, right? So it's going to be, my next diagram will be, okay, of this sort. Okay, just the V itself, right? So maybe I'll start writing. So this is FNT2, okay, connected. I just write it like this. We know it's projected on doubles, okay? This one is just Vn. What else? What about VNT2? You think we have it? We will, okay? You know, it's like this. This is T2, and you see I have 4 lines sticking out, okay? That's VNT2, projected on doubles. It's connected. Must be connected with at least one line. Okay, what about T2 squared? Do I have something going? Good, maybe it's good enough. Okay? Because it is, well, maybe it says that there is a possibility, there is a yes. Right? And there is a yes. Look, you can do this. Okay? Or you can do this. 3 lines one way, 1 line the other way. See that? So V and T squared, T2 squared. Okay. Do you think I need to worry about T2 cubed? No, and I'll show you why not. Yeah, you know, yes, the answer is that you don't have to worry about it because T2 cubed has 3 T2s, each T2 has 4 lines. Okay? And you have not enough lines in the V to solve, to deal with it, right? So what you have there is, if you want to look at 3 T2s, just to sketch it, so connected, V connected to T2 cubed means that you have to send at least 1 line to each T. That's what the word V and T2 cubed connected means. Okay? But I have to end up with 4 external lines. Now there are many lines here. Okay? 3 here left, 3 here left, and 3 here left. Okay? And 1 here left. See? Too many. Well, I can try to fix it a little bit. How about if I turn this line over here? But I still have 2, 3, and 3. 2 plus 3 plus 3, that's 8. That's quadruples. Projection quadruplets are there. So CCS DTQ will have this guy. CCS DTQ will have this, but not CCSD or CCD. Okay? Because I do not have enough lines in the V. So that means that I'm done. Look, just that system equation is trivial. So all we need to do now is to just derive them. Right? Okay, so let's see. Okay, do I need to keep this guy, or you are convinced that I can do it? Okay, just remember, that is how you go about it. Okay, so we have only 3 contributions. Okay, we have phi, ijab, fnt2 connected, vnt2 connected, and 1/2 vnt2 squared connected. So there's quadratic term. Okay, phi 0 equals 0. That's how the system looks like from the outset. Okay, so let's now start going to the diagram. So for this guy, we already have skeletons. So all I need to do now is to fill them with arrows. Okay, so I'll do it now rather quickly. Okay, so what we have is the first diagram that you see there. Okay, we'll end up with 2 diagrams. Okay, maybe I'll separate them. I will separate them with some lines or something. Maybe I can use some blue line or something. Okay. Because you can see I can do the following. I can have these lines going this way. Okay? Or I can have them going the other way, right? But before I do this, actually, you know, you can imagine I can have the flow here different. But I'm not going to do this just yet because I want to now teach you one trick, which is universal. I need to label these lines. So I'll do a canonical ordering. AI, B, J. Right? That line will be called M. My advice to you is, for external lines, use A, B, I, J. For internal lines, use higher symbols, always. In this way, you will remember that A, B, I, J are fixed. E, M, and so on are internal lines which are being summed over. Okay? Is this clear? My notation will now reflect really what I'm doing. A, B, I, J will be fixed, those are projections. E, M, higher lines will be. But now the question is this. You remember when I was explaining to you the rule of sign, read from the diagram without the projection, I told you have to sometimes watch out if the permutation of labels will produce a new diagram. Well, look, if I flip A and B, do you think I get a new Hugenholtz diagram? If I just simply call this one, this line B, and this line A, do you think that this is the new Hugenholtz diagram or not? No. But what about if I do this? So now let me show you something. What if I call this J and I? Is this a new diagram?
Yeah.
You see? So one skeleton produces two because indices are fixed. I don't want to draw so many diagrams. So we'll have a symbol now called symmetrizer of diagrams. I'll write it with a script S, okay? Instead of writing two diagrams, I'll draw one. Okay? So A, I, B, J, M here, and I'll stick that symbol S. For occupied states, I'll put this on top, Sij, you'll understand why. And what it means is 1 plus interchange I with the J. So instead of drawing two diagrams, I'll draw one diagram and I'll stick a symmetrizer of the lines. So that I can draw one to represent two. Okay? You will see that it's very beneficial because there is a simple rule of the sign versus the symmetrizers. There is one-to-one correspondence between the symmetrizers and anti-symmetrizers expressions. Okay, so that's my first diagram of this type. Okay, so this is all F and P2. There's another one. Okay, what's the second one? The second one I already mentioned. What it's going to be? Okay, it's going to be A, I, B. Sorry, it's going to be the other way. Sorry, too high. This way. Okay. Right? So now we have J line here and A and B line here, and this will be then E. So you're summing over E. And again, is one diagram enough, you think? Not really, because flipping I and J now is okay. But if you replace this index by B and this index by A, that's a new diagram. So instead of drawing two diagrams, I'll say symmetrize this picture with respect to A and B. Symmetrizer AB is unit operator plus interchange of symbols A and B. Okay, so in this way, instead of drawing two diagrams, I'll draw just one. Okay? Is that clear? What I'm doing? Mm-hmm. Okay. So now we're done with this part. Let's go to the next one. Well, V is easy, of course. So okay, so let me do V is quick, right? So Vn, of course, that's just you have to label this with A, I, B, J, and you don't have to do anything anymore because flipping indices doesn't produce anything new. Then we have V and T2, okay, contribution that we have there. So we have, you can see we have different situations. Those are the diagrams that we see over there, okay? And we have, particle, hole, and particle-hole combinations. So there will be diagrams that look like this. They all have the same sort of overall structure. Okay? But now you have a lines flowing this way, lines flowing that way, and lines flowing in a particle hole way. Okay? Now we need to label them. For the internal ones, we'll use symbols E, F, M, N. So this is M, N. Okay? This is E, F. And this will be E and the companion M. Okay? What about external lines. Well, we certainly know that one possibility is to put here, say, yeah, of course, ij here and ab here. We can put ij here and ab here. And I can certainly put, say, ai for the ones inside and then bj for the ones outside. But the question is, do I need to consider permutation of indices to produce new diagrams? Well, in the first case, no. Because if I flip I and if I call this index j, this I, that's not a new diagram. So nothing here. Same here. No. If I call this b and this a, that's the same diagram. But here, there's a change. Because if I replace I by j, that diagram is a new diagram. Because j is fixed and I is fixed. Okay, so here, and the same with AB. So here you have two symmetrizers of the diagram. Meaning that this one picture represents actually 4 diagrams. Right? That's how we do it in combinatorial theory. Okay, so we're done with the linear stuff, so I guess we're almost there now. No, non-linear ones. Yeah, I was optimistic about the time. Is tape still running? Oh, I think now is it is 15 minutes, so my 10 minutes is shifting, but let's call relativity. Okay, so Vm theta squared. But I think I hope it's valuable for you. Okay. Because those are the inner, pieces that, are not discussed in normal classes. Okay, so, what I need to do? I have 2 skeletons. Remember, I have them here. So I have this and this. So let's start with this one. A very interesting one, right? So we have T, this way, and that. So what can we do with it? One thing I can do is, send lines in, that they will continue here, because they always, remember, 2 lines in, 2 lines out. Okay? You just flow through a diagram and you leave here. And then I just have to label them. So, for this, I'll call this AB, this will be IJ, okay? And this will be, say, this will be MN, and this will be EF. Remember, A, B, I, J are fixed. M, N, E, J, E, F are free. Do I need to draw more, you think, for this guy? No, because, if I replace this, if I call this J and this I, this is a Hugenholtz vertex. No new diagram is produced in this one. Remember, it's all Hugenholtz. So no need to do it. No, now let me ask another question. Should I flow lines in the opposite direction? No, because I can obtain the same diagram by flipping 180 degrees, right? So I don't have to do that. But there's another possibility. The particle hole possibility. Okay? This one. So now you have particle hole, particle hole, particle hole, particle hole. That's the tricky one. Okay, so we have A, I, B, J, E, M, F, N. The question is, do I need to put more? Well, if I flip A with B, it's a new diagram. It is a new diagram. Because if B is here, so let me actually, this case it requires now special attention. Okay, I'll try now, simply, rather than guessing, my advice to you is don't guess. Draw them, honestly, all permutations, okay? It's a labor, do it. Because if you don't, and if you don't have enough experience yet, you may miss. Even if you have experience, actually, you can miss. So I'll say, here I would be a little bit more careful. Of course, when you do it sufficiently many times, you develop a lot of intuition, right? A lot of sort of, hands-on experience. But, I'd rather be careful. Okay, so what I will do these permutations, okay? So let me try to I will keep A and B here, but I flip J with I. Well, that's certainly a different diagram. Because you see the line, we have different indices at different T2 vertices, right? So we have, say, this is still EM and FM, okay? But I can try, so this is, let's maybe mark it. This is, I flip I with J. How about if I flip A with B? That's the point I'm trying to make. So let's just do it. So when I flip A with a B, now this will be B, this will be A, this will be I, this will be J. Okay? And let's just do, before we talk about it, one more, right? Which is the last case, you flip both.
That'll be the same, right?
Yeah. That's exactly right. But you see, you cannot see this easily, at least without getting yourself trained for a longer time, that this is the case. So if I flip both, this is going to be Bj and Ai. You see? Okay, still EF, EM, Fn, EM. But you remember, EM, Fn can, I don't even have to write them for this kind of analysis because they're free symbols, I sum them over. Okay, you can see that we, in principle, we should consider 4 permutations, 2 symmetrizers, but only 2 of these diagrams are non-equivalent. We are not drawing non-equivalent diagrams. Sorry, equivalent diagrams. These 2 diagrams are the same. Because if I flip this, okay, I get this diagram. I'm talking about the topological flip, just flip it as a geometrical flip. Okay? It's the same diagram. Because lines E, M, F, N are free. Same here, these 2 are the same. So although in principle there are 4 permutations, I am now learning that this diagram has only 2 diagrams behind it. So let's register that information. Okay, I'll do it here. So E, M, F, N, A, I, B, J. But I'm going to put a symmetrizer. Now we have to choose. What did I choose? I don't know what I chose. It doesn't matter actually. Let's stick with my notation here. So I put SI. Okay. All right, that's enough. That gives you all diagrams. So there are 2 diagrams out of this case. And I write only one with the symmetrizer of the diagram. Okay? So remember, what we have on the right hand side is just an analysis. We don't have to worry about it. So now the last thing are the other diagrams which have is the composition of lines, 3-1 between the T2 squared vertices. I'm talking about this. Okay. Let's see. I don't have to touch this. Actually, let's see. I think I have to go there. Okay. What I'll do here, I guess we can already erase most of it. Okay. I just need the skeleton we are dealing with. Okay. We already covered all these other cases. Okay. And we have this skeleton here. This skeleton will produce 2 possibilities, right? So let's just deal with them. Okay. You can. That's a gross exaggeration. Okay. So. Okay, so let's call this AI, then let's have this line first coming in. So it's going to be, say, J, right? Coming in here, and leaving as a B, okay? So now the line, one line is in, one is out. So you have E, M, and that N, and this one is F, okay? That's the line. And now, do I need symmetrizers of any kind, of diagrams? Which one? Can you tell me right away now?
A and B.
Exactly. So I need this symmetrizer, and I'm done. This is 2 diagrams, really. Okay, written as well. Okay, and the final picture is the particle Hall complement of the last one. Okay, so now we have still AI. I'll keep that, but instead of flowing in, I'll be flowing out from here. Right? So I flow in here. Okay, so everything is in reverse, right? So one line goes here, one line goes here. Okay, so we're going to call this J, this will be B, this will be now N. Let's just write this companion terms. So again, E, M, F. E, M, F. Okay? And do I need anything?
Yes.
Yes,
IJ.
for IJ, exactly. And this is the entire system of CCD diagrams worked out. So now we can erase it, we just have to read them. Okay? Let's see. Is everything there? Okay, what I'm going to be doing this. I'm going to be writing equations and throwing away things that we completed, right? So I guess I have to start from the top blackboard there. Okay? And okay, read this. First of all, I will erase this definition. I hope that we are already clear on that, right? We have only one diagram here, so I'll erase those 2, okay? Carefully. we have to read this diagram. Of course, for each diagram, we have to read the corresponding Brandow. So what is the Brandow here?
You can skip Brandow and just tell us the signs if you want.
Yeah, well, okay, but it's good to, yeah, you know, this will be quick. Okay, I'll just copy, okay? How about that? Without talking too much. Okay, so let's see, where is my, there it is, yeah, okay. No, so that you see this diagram, because, you know, that's the, yeah. Okay, that's how it is for the first one. Okay, so you have, that means that's right. A, I, B, J, M, symmetrizer over Ij. Okay? The weight for it is, can you tell me? Weight? 1. 1. A, B, I, J are fixed. So the weight is 1. Okay, weight of this diagram is 1. So I'm going to copy that here. Weight is 1. Sign is, you can tell me?
-1.
-1. 1 internal line. No loops. Okay? Sign for this one. The question is what's going to happen with, how is this going to affect the sign? But we already know the Ij permutation will change the sign by 1. So the symmetrizer will become an anti-symmetrizer, okay? You can already see what's going to happen. Because I told you this rule, you know, -1 to the L plus H plus permutation signs. Okay? So we'll come back to this. Now the next one, so I can erase now, okay? I'm going to start reading this. Alright. Next one. Next one is the same picture. Okay, let me now. Okay, A, I, J, D, E, symmetrizer AB. Okay, weight is 1, sign is 1. For the canonical form, not for the other one. Okay, let's erase, continue. Then we go Vn. The next one is Vn, right? So Vn is just the familiar shape. A, I, B, J. Okay? No need to permute any indices because this is really Brandow representing 1 Hugenholtz. Okay? So weight is, what is the weight? 1 over 4. So sorry, 1, because it's all fixed. What am I saying? Weight is 1 and sign is 1, right? No loops, no internal whole lines, no nothing here, right? So, okay. So we continue. Okay. What is next? The other three. Okay, so what you see there is this. T2, V vertex, okay, and, right, so this is the first one, okay, and we have I, A, J, B, M, N, and I'm done, and I'm talking about diagram here. Okay, so this is going away, this is going away. This is this one. Weight of it is 1/2. M, N are equivalent. Right? A, B, I, J are not by weight, but M, N. You have to watch for the loop. It's free. Those are free. So in the skeleton, they don't exist, right? Sign is, of course, +1, right? Next one. Similar picture. Not the particle form of it, right? So we're going to have A, B, I, J, okay? And then we have E, F, okay? And again, weight is 1/2, because EF is equivalent in the Hugenholtz. You see the Hugenholtz there? 1/2, okay? And the sign is 1, okay? And the third one, maybe I'll write it here as well, so we have all three in one piece. Let's see, okay. So you have in and out, and then the other way around, so it's particle hole, right? So we're going to have now out here and in here, okay? So this is going to be D, this is going to be J. Remember, in this expanding, canonical expansion, I always match I with an A, J with a B, and then I stick the symmetrizer to take care of the rest of the sign contributions, okay? So here we have the two contributions, Sij times Sab, right? Weight is 1, nothing is equivalent in this diagram. What is the sign? -1, right? We have one internal whole line, because here we have M, here we have E. Okay, so we're done with these, and now